This example will be about interference, fixed frequency stations and frequency hopping stations, and we will treat collocation, interference and remote interference. To start with the collocation interference case, this example is about a ship with 6 radio stations on it. There are UHF stations, VHF stations, 2 of each, and they are separated 5 meters horizontally, and the vertical separation between the antennas, let's check what that is. VHF1 is at 7 meters. VHF2 is at 8 meters. So there's a 1 meter vertical separation, and it is the same for the UHF stations. So let's check this installation for interference. I mark all stations, select the collocation interference tool, and it starts with showing the stations and their frequencies, transmit receive frequencies and the bandwidth and so forth. So to calculate the interference, I press calculate button and I'll expand here. Worst interfering victim, at least the one with the most interfering cases on it, is UHF1. So let's start to check what that amounts to. This interference type are 5 cases of it. Co-channel or adjacent channels interference. There's no co-channel here, so it is adjacent channels. And the worst interference condition is from the HF transmitters, actually. So they contribute with noise, or the receiver, UHF receiver, does not suppress sufficiently. So a quick attempt to fix this situation is to put filters on the receivers and perhaps also on the transmitters. So let's start with the receiver 1. I'd put a collocation filter on it, and there are a few selections here that are suitable. This one has a selectivity appearance like this, so it attenuates at most 60 dB, 4 megahertz away. So it is quite a good narrow filter for this purpose. So let's use that. And now it says station data recalculate. So I recalculate. And we still have interference on UHF1. Let's see what that comes from. Yeah, it comes from these stations, and they also contribute with a lot of interference from the transmitters. We have cleaned up the receiver of UHF1 now, so let's continue with the receivers, the transmitters here, VHF1. Similarly, let's put a filter on it. So we have one, yeah, I'll use the same. This 400 megahertz, as it says, it is tuned anyway for the calculation purposes. It is tuned automatically to the assigned frequency of the transmitters and the receivers. So we can just put it on there and see what the result is. For the HF stations, I will put on an HF collocation filter. It has similar characteristics, or actually it is much narrower, because this is so much lower frequency, so it's possible to make more selective filters there. Okay, and lastly on HF2. Okay, so let's recalculate and see what still is there. Yeah, we have some interfering cases. UHF1 that we started with is okay now. So what about this one? It is interfered with by UHF2. The amount of interference is about 5 dB. It has a margin minus 4.6 dB, and this is in effect the noise increase experienced by receiver VHF1 due to the interference from this transmitter. This UHF2, let's put a filter on that one also. And VHF1, did we put a filter on it? Yeah, it has a filter already. So now recalculate. Now the list is empty, so we have cleaned up the situation completely. There is no longer interference. We can view interfered receivers or interfering transmitters. There are no interfering transmitters either, so this is a good situation now. The collocation interference tool has lots of settings, and it considers adjacent channels and co-channel, of course, intermodulation, harmonics, receiver blocking, intermediate frequency, feed-through, and image frequency. Harmonic orders up to 13th, intermodulation order up to 13th also, and maximum number of concurrent transmitters, also 13. It's very seldom that these numbers have to be used with this high order of intermodulation and this large number of concurrent transmitters. But the capability is there, so it can be used. RAP also has a feature of minimizing interference, and this is used to create interference-free channel plans. In a co-location situation, that may be quite difficult to find frequencies that are free from intermodulation and adjacent channels interference. So RAP can automatically analyze, synthesize, and generate such interference-free frequency tables. Okay, so this is a clean setup now. No inherent interference with between the transmitters and receivers. So let's check what happens if we put another chip in the vicinity, and that is a quick operation. To create an identical chip, I just make a copy of the platform and drag it somewhere there, for instance, perhaps, well, these two are very close to each other now, so let's make a collocation interference calculation on this setup. Okay, there are two cases of interference on each of the receivers, and it is quite evident what it is. It is co-channel, since they are identical twins. One ship is transmitting on 130 megahertz, and the other tries to receive on that frequency, so there will be a very large amount of interference between the two if they try to operate independently. So that's quite evident, and similarly the blocking effect of the receiver. So that's not a real surprise. This situation cannot be cleaned up apart from changing frequencies or moving the ships apart. Let's continue with another example, and now it will be remote interference. So I'll close the ship project. I don't save the changes, and let me move the windows so they are clearly visible. This project contains a number of stations. The ones that are called 8FH are frequency hopping stations, and they operate on a 10 megahertz wide band, 40 to 50 megahertz, with a channel separation of 25 kilohertz. So that's 400, or actually 401 frequencies in the hopping sequence. 40 and 50 megahertz are both included in the hop sequence, so it will be 401 frequencies. The antennas are at 24 meter above ground level, radiated power 40 watt, 16 dB watt. We'll have a particular look here at this site where there are 4 stations. So we'll zoom in there and see what it looks like. This is the site then. They are separated by 10 meters. Each square here has a 5 meter side, so they are located in a square of 10 by 10 meters. FF03 here is a fixed frequency transceiver, operates in the middle of the hop band, 45 megahertz, and the other 3 are frequency hoppers. So let's check this for interference, and I will use the remote interference program or function of RAP. It accounts for the interference of the nearby transmitters also, but it does not consider intermodulation and receiver blocking and a few of the other things that are particular to the collocation interference function. Calculate the interference, and here we have a mix of fixed frequency and frequency hopping stations in this project. What the result now shows is that the sensitivity limit of fixed frequency 03 is minus 110 dBm. It experiences interference at minus 48 dBm, total interference, and let's have a look at what that is. It is fixed frequency interference from FF01 and FF02. They are remote from here, so it may very well not be interference. It may be the wanted signal actually that it is communicating with. But the interesting thing here is the frequency hopping interference. There's a 100% probability in time that the fixed frequency receiver will be interfered with at a level that is higher than minus 110 dBm. So this means that the sensitivity is severely degraded for this for the FF fixed frequency receiver always, or at least when the frequency hopping transmitters are transmitting. Let's check the individual contributions. P frequency hopping is 100% from the nearby FH21 and FH23. They are the closest ones, so they would give most interference. FH22 is the one diagonally opposite, and the distance is slightly larger there, so the interfering levels are smaller, and therefore we can see some reduction here. But of course this can't be. We have to do something, and the general recommendation in a situation like this is to test with filters, and of course we will use that. And this bandpass filter, 70 megahertz, has a selectivity characteristic that is reasonable to implement in a frequency hopping filter that tunes along with the hopping radios. So we'll make use of that. And I'll use that filter on all stations that are involved in this collocation situation. And we also need to put it on the fixed frequency receiver. So there we are, and now we recalculate and see what improvement we gained from using this configuration instead. Now, the total probability from all the frequency hoppers of interference is about 25% in time. So each of them contribute about 8% to the interference. And of course, this depending on the coding, error correction coding, and the signal processing of the receiver, this may be okay, or it still may be too much, but that depends on the quality of the coding, or how much redundancy for the data transmission and whatever that is available. The others, the more remote frequency hoppers, give each this contribution 0.249%, and that is just 1/401, since they hop on 401 frequencies at any instant in time. Looking at a single frequency, the probability that the hopper is on that frequency is 1/401. So that's why we get that value. And again, the fixed frequency here, interference, that level is calculated, and it may be interference if they really are supposed to operate in different nets, or it is actually wanted signal level if they are in the same net. Then we'll make a third example, and this is to demonstrate interference analysis for I close that, general EMI emitters, electromagnetic interference emitters. In this case, there are two receivers, one at 60 megahertz, one at 400 megahertz. Then there are four what we call EMI emitters, electromagnetic interference, and they are defined according to the two. These two, RE102 ground, it means radiated emission 102, and that is definitions from MIL standard 461. It's narrowband definition, broadband definition. So the spectrum of this is taken from a transmitter that has been that we have created, RAP EMI RE102 ground, Navy, mobile, and well, whatever it says there, Navy, mobile, and Army narrowband. And this is the spectrum with frequency and level, and it defines the spectrum of that emitter according to the MIL standard. These two are European civilian standards according to EMI reference standard EN 55022, Class A narrowband. These look like this, and that step may be that at frequency, the reference bandwidth, the measurement bandwidth for the standard is changed. The separation here is 5 meters with receivers in the middle, and the other, all the emitting, the interference emitters are around. Typically, the 55022 standard can be often applied to standard computers, PC computers, desktop laptops. So it is a representative situation to try to receive radio signals, and only 5 meters from the antenna there are computers. So let's check the interference that these receivers will be subjected to. Okay, having a look at the 60 megahertz receiver. We'll expand this a little. It can be seen here that the worst interference is for the broadband definition of RE 102, the MIL standard. No, I read that column. That was in error. It's the margin we should read. Of course, the worst is the civilian standard narrowband definition of the standard. So actually, the computers are allowed to radiate in narrowband radiation that will degrade the sensitivity of this receiver by 53 dB. The broadband noise will degrade, or may degrade, we should say, because this is what they are allowed to radiate. They perhaps do not radiate that much. And at 400 megahertz, it's also bad. But it can be seen from here that in order to have a reasonable chance of good reception for the military situation, with computers being in a staff headquarters, for instance, quite near the receiver antennas, an EMI standard of the severity or stringence of MIL standard 461 should be selected. The civilian standards are simply not sufficient. If there are these computers in this staff headquarters, they will produce a lot of interference if they are installed just without any protective measures. If they are installed in shielded enclosures and very careful shielding and decoupling of connecting cables, then it may be okay. So RAP has a lot of capabilities in analysis of interference, both remote interference and collocation interference, including consideration to radio transmissions and generally defined EMI, electromagnetic interference emitters.